Hello and welcome here out of the forest. So my name is Sven Ruppert and I will explain you the core concepts of functional reactive with core Java. So if you're interested in what are the basic principles and how to start with the functional and the reactive coding without adding any other library to your project, stay tuned. What the basic idea of the functional programming and the reactive programming? So you can hear a lot about it, you can read a lot about it, but the basic principles for the functional programming are not so complicated, and this is what we want to achieve with core Java during this talk. And let's explore the basics here. So the basic of functional programming is, for example, that you have a lot of immutable stuff. So if you're creating a state, if you're creating an instance of something, then you don't change it. Means you don't have this getter and setter. You have just getter for attributes if you have a holding class, and initially you're giving via constructor, for example, the values itself. So this immutability. The other thing what is part of the functionality is that you try to reduce all actions or all changes, transformations to one input value transformation to one output value. So this is a core functional idea, so that you're just dealing with input state that must represent everything, and then you have something that is happening, and then you have one output value. Now the concept of the functional approach is, for example, that you try to catch all exceptions, but you're not throwing exceptions. And one is, for example, that you don't have this construct of a null. So if you have an invocation of a function, you will always get at least one result. So you have different paradigms here. And we want to explore step by step different things, what is already existing with core JDK 8 and later, or what we will get by ourselves. One thing I just want to mention is that during this talk I will explore a little bit about this functional behavior in general, but I'm not following the strict academic rules that will define the functional world. So here I want to focus on pure practical approaches. Okay, before we are starting creating our own data structures or mechanisms, I want to highlight what we have already inside the JDK. And with JDK 8 and above, we have this construction of a functional interface. Why I'm talking about functional interfaces? So, first of all, functional interface evolves over the versions of the JDKs. For example, in JDK 8, we have just the functional interface itself. So it means an interface with default implementation and just one method that must be implemented. On the other side, with JDK 9, we got finally the private methods inside this interfaces, so that we can start structuring even inside the functional interfaces the code a little bit more than just having one big method here. On the other side, we have these static methods inside functional interfaces or inside interfaces that we can use as a factory for instance of functions, and this we will see is one of the places where we can put all this code to create instances of the functions. And yeah, this we need a place somewhere, and we don't want to go over inheritance, we don't want to go over instantiation itself. So functional interface or interface in general, they are good as a place, as a starting point as a reference where you can start getting functions and all this stuff. On the other side, just have in mind for the API, if you have a static method and you're have something like an inheritance, then you must make sure that or the thing is that you will see the original interface where this method is. So even during the inheritance phase, this static method is not going to the other classes. So if you have interface A, interface B, B is extending A, and in A you have a static function or a static method, you can't invoke interface B dot static method. So you always have to go back to interface A and then invocation of the static method. This is just as a heads up so that you have a clean API and nothing is bleeding out of your API if you need a structure of different interfaces. So this is one thing. The other thing is just if you have functional interfaces and you have different inheritance paths, so class A is implementing interface and class B is implementing the interface, and then you're just merging. So if you have this diamond in your implementation or in your inheritance, then you must make sure that you are deciding which one is the default implementation or the implementation that is used. So this is highlighting if you have a method inside an interface with a default implementation and you're merging different signatures that are just the same. So the compiler will just break and will let you decide which one is the default implementation. So even inside inheritance with default implementations, there is no way to create this diamond inheritance. So you are sure and safe at this in Java anyway. So anything else for these interfaces? No, just have in mind that this functional interface is a base for the lambda constructions, and this is a syntactical sugar we are using extensively. But everything without this lambda construction, so without this syntactical sugar, you can do with previous JDKs as well. The first thing we want to create now is something around the topic null, because null is something that everybody is complaining in Java about, because it's breaking the semantic of this functional world. So one input, one output. And how to get rid of this one. So with JDK 8 we created, or we got inside this API, the optional. The optional is a holder of type T. It means you have an instance of an object and it's typed with whatever's inside. And you have different functions or methods you can use here. You can use, for example, if present or not, map something, or get it or else, so all this stuff, so that you can ask if there's something in and then getting it out, or you can start transforming it, or you can just ask if something is in, otherwise do something else. So there are a few things I don't like with this optional. A few are just a few things changed over the JDK. So for example, this if present or else. So now you have the possibility to say if there's something, do something, otherwise do something else with two lambda constructions. And we have get or throw and all this stuff. So we have different improvements with the API, but the main disadvantage of this optional is, first of all, it is final, so you can't extend it. And the other thing is that it's not symmetric. So you have something like if present, but you have not the method if absent. And this leads just to ugly code outside. So more or less, we have to create something by ourselves, because we want to add the information. If there is an exception, then I don't want to give back just this null. I want to give, for example, some information what was going wrong back. So not just object with this holder with a null. Means that I'm creating now something else and I'm calling it result. So result is API compatible as a drop-in replacement with an optional. So the good thing is you can just change import statements and then you can use your own implementation. This is something because maybe you want to get rid of it or you want to extend it or whatever. So make sure that this is API compatible to an optional if you're creating something by yourself. The next thing is I'm just making it symmetric. So if present, if not present, or if absent, all these methods I have in a positive and a negative way, so that I don't have this negation somewhere, or that if something, do something different. The next thing that is important is that you have the possibility to have a false. So how to deal with this false? So you can ask, do you have a positive? Do you have a value? But if you don't have a value, do you have some other information? And this is exactly the stack trace or the information about the error message. And you will get a result of type whatever you have, but you will get a string out of it if it is, for example, not valid if you have an exception. So you can ask, do you have a value? No. If you don't have a value, give me information what was going wrong. So all this stuff. One additional what we need later is that I created just a reactive API additionally to this optional, because we want to extend all these transformations. Otherwise you are just stuck in this object hierarchy, on this class hierarchy. And this is one thing that is mostly not nice with all the other functional implementations. So you're getting a lot of functional stuff with other libraries, but you have mostly your whole own typing system. And then you have this ugly layer between the core Java usage of this library and then back to the core Java world. And to get rid of this one, if you're creating something, make it like a drop-in replacement. That's really, really important. The next thing I want to cover is exceptions. So in the functional world, you don't want to throw exceptions, but you have to deal with exceptions because the language itself is dealing with exceptions. So it makes no sense to ignore them. So one approach is just take as many exceptions as you can, so catch them all. But if you have by yourself the challenge that you have to deal with an exception because it's base of the Java language, there's a runtime exception or whatever, then you have to wrap everything more or less the result inside a holder like optional or result. And your function is now something like a function from A to B, but A to result of B. Because the boring part with exceptions is that you always have to write this try and catch, and try and catch is so repetitive. So you're writing always the same code, and this is one thing that you should try to extract. And if you're extracting this one, the approach is quite easy. So you're going over default implementations, putting there this pattern with the try catch in, and then the method to implement is just inside an invocation inside this default implementation. And with this you can create functional interface again, and with this you can create lambdas again. So now with this approach we have now checked functions. If I've checked functions with the same approach, what I have is, for example, checked suppliers or consumers, because here I do not have the type A to type B transformation. I have, for example, void to something of type, or something to void of something. So I have all this done. So consumers, suppliers, and so on, everything is in a checked version available as well with this approach. And the only thing you have to do is extract this try catch block. And the good thing is you can go always back from your checked functions back to the core Java functions, because you have this indirect mapping to this holder, because you have to deal with a exception message, for example. So if you have the checked function, you can always go back to function from A to result of type B. That's it. And with this you can remove a lot of boilerplate code. So next would be that we're going a little bit to this theoretical approach. What's this functional world, and what are the typical mistakes that what I see if someone is coming from the pure object-oriented way. So for example, if you have a stream, and inside the stream you have this filter for something, and you want to filter, for example, a string if it contains A or B or whatever, you would have somehow in this stream construction this predicate that's asking is this string containing A or B or whatever. And if you're extracting in a regular way, you are coming quite far through this point where you have to deal with this final construction, because the string must be final and it's part of this predicate and so on. But here the first approach is, don't say what you want to have or what you need, so describe what you need. And the description here is, I want to create a predicate that is able to decide. And this means if you're just writing down, I need a predicate asking for A or asking for B, you should describe how to create this predicate. And this is a function. So the input value is what you want to compare with or search for. And the result will be an instance of a predicate. And now what you have extracted is the way how to create the predicate. The dynamic part is a value, so you want to search for or you want to ask for, and now you have a function again. So the input is what you're looking for, and the output is an instance of a predicate, and this is exactly what you need. So this typical extracting is not working, so you have to describe it in a way. So you have to think in transformations. Let's talk about functions and how to extract this one. So if the way to go functional is always pushing abstraction to the limits, means that you try to find the maximum generic way to describe it, so that you have a lot of atomic operations that are building for you the specialized operations. And we have this function that's adding 2, the next one is adding 10, the next one is adding 5 or whatever. So we have different functions here. So what would be the right way to extract this behavior? So the only thing that is changing here is the +2, +10, +5, plus whatever. So how to deal with this? So what I want to describe is now how to create a function that is able to add something. And the target would be, we have a function with an input value, 2, 5, 10, whatever, and the result is an instance of a function, and this one you can use. And then you can go to this compose and then mechanisms, but here just be aware of Java is better with and then instead of compose. So everything that you want to add before a function will have challenges with the typing, because the type interferencer should expect what is possible that is coming in front of and so on. This is not working well. But if you are doing it with and then, so if you're adding functions one by one after another, the type interferencer is way easier to handle, because you have an output type from the previous function. You have with this defined input type for the next function, and then the type interferencer is working quite smooth. Okay, the next thing I want to explain is a term currying. So if you're reading about functional programming, they're always speaking or talking about one input value and one output value. And even the bifunctions in Java are not pure functional at this point. And you have to deal somehow with more than one input value. So how to deal with this one? The approach is the following. So if you want to reduce by currying the complexity of a function by 1, means from 2 input values you're reducing to 1 input value. And this is the main thing. If you have done this one, you can do it from all complexities to 1, because this is just a symmetric behavior. So how to do it? If you have 2 input values and you have 1 input value, what you have is more or less a transformation first with the first input value to a function that will need the next input value and will give you the final result. The function that you will get out of the first transformation is holding the first input param as a constant inside. So if you have a and b will lead to the result, would give you first a function with input a will give you a function that will give you the result based on b, and internally it has already a. So this is currying. That is not so difficult if you're just thinking about holding instance inside. So the nice thing here is that you can transform a bifunction to a curried function, and this curried function you can transform back to a bifunction. And with this symmetric behavior, you are able now to transform from bifunctions, trifunctions, whatever functions, so that you can map from the pure object-oriented method signatures to functions, and these functions you can transform to curried functions. Then you're in a pure functional environment. Inside this one you can do everything what you want and what's possible with a pure function with 1 input value, 1 output value, and then you're just currying back until you reach the level you need, for example, as something that you use to connect to the pure object-oriented world, or to different inputs at the same time. That is the main thing about currying functions. So 2 or whatever input values are just a cascade of invocations, and every interim step is just holding the variable that was given before, and in the end you can just invoke it with the last param. That's currying. Okay, one other thing that you can read quite often in this field of functional programming is the term memoizing. What does it mean? So if you're invoking a method twice with the same input params in Java, you will get 2 times the same result, but different instance. And in a functional world, it means if you're invoking 2 times a function with this same value, input value, then it must give you exact the same output value again. And this means even the same entity, not only the same value. And here, to reach this one, what you could do is you have a method, and inside this method you're holding, or you have a function, and inside this function you're holding all values, all input values inside a concurrent hash map, and the value of this key is the result. So you're getting the value A, then you're calculating it other way around. So you're getting value A, then you're checking inside this concurrent hash map if this value is already existing. If this key is not existing, you're calculating the value, putting this key value P to the concurrent hash map and giving back the calculated result. Next time you're invoking with A, you're just looking inside your concurrent hash map. If you have this already, yes, you calculated it once, and then you're just grabbing it and giving this again out as a result. So what you reached here is first of all some kind of caching. So if you have calculations that are a little bit more CPU intensive, you're just saving time because you're just calculating everything once. Have in mind that you're dealing with memory, so for sure. But on the other side you have this behavior, this pure functional behavior, because you're giving exactly back what you calculated once. So exactly the same object reference is giving back. This is a pure functional behavior for sure, but have in mind that this makes only sense if you're giving back immutable instance. If you're giving back mutable instance that you can change, this is just pain. So this is just not working. So have in mind that if you want to deal with memoizing, just make sure that you're using here at this point just immutable types, so types that you are creating once and then they are never changed again. So this is the term memoizing. With this memoizing stuff, you can do some quite cool stuff. For example, if you're extracting this like a method reference, so object name double point method reference, then you can use this one even for legacy code. So because if you're looking at a method signature that you're extracting at the method reference, it is the same like a function by function or whatever. So with this extracting a method reference from even legacy code methods from a dedicated instance, you have the functions, then you can curry or uncurry it, and then you can add this memoizing stuff, so this behavior, and then you're giving back the old reference. What you are doing here is just, you have legacy code, you are not touching the original implementation, but you're adding something like caching to this implementation. This is quite nice. Maybe it helps, maybe it's just nice to know it, but you're never using it, but it is possible. Have a look at method references, currying, uncurrying, memoizing. This is a really big beast. Okay, one of the next things we want to see is how to deal with decisions. So in Java, we have this if statement, if then else, we have case, we have this construction with the asking sign, and so on and so on. So they're evolving over the time inside the JDK, so this is improved step by step. But one thing is, we want to have it in a more functional way, and there's one thing that is, well, if you have whatever complex tree with this if then else construction, for example, you can remove or you can reduce it in a way that in the end you have just a list of predicates or decisions and then a corresponding calculation. So whatever tree we have, we are reducing it to a list. If you have this one in mind, then we can make this predicate that is giving, yes, I'm the right path in the tree now, yes or no. This can be as complex as we want and want to have, and the other thing is the corresponding calculation is completely independent from the path before. So we creating now something like a case, and this case will have a pair, and the first one is a decision, yes or no, and the second one is a calculation. And with this, I can build now in a linear list a whatever complex decision tree, because I'm just saying, if I have input value A, B, and C, and not D, then do this one. If I have whatever, and then calculate the next one. And this is a very convenient and a very compact way of deciding, and this is a way that is easy to maintain, because we all had this somehow this complex if then else case whatever things, and then what is the right path and how to test it. And with this case we have just the predicates that are saying yes or no. We can test very easily. We have the calculations completely independent. We can test them and we don't have to make them as part of the structure. And just a combination is a linear list, and then we can just go over the decision tree and say A, B, C, D, E, and so on, and the maintenance is super duper easy. And if there is nothing inside this A or B or C or whatever decisions, we always need a default. So the last one is a default. So if nothing before is actually saying true, now I'm switching to this calculation. We have a default calculation, and this can be whatever we want to have. Okay, in the beginning of this talk I spoke about functional and reactive. So far we saw a lot of functional aspects, so how to deal with this immutability, the exceptions, how to make decisions, how to deal with null, all this stuff, and how to memoize and query function. Now it's time to talk a little bit about the reactive, the core reactive part, before we are merging both. And the reactive, what is the basic principle of the reactive part? It means that if you have some input values and you know what should be calculated, then you are just going to this instance that's able to calculate, giving the values and saying goodbye, I'm now waiting. So, or I'm doing something else, so I'm not blocking at this. So you're giving the values, then you're decoupling, doing something else, and then if the result is there, this guy will come back to you and say something. It's this Hollywood principle. No, don't call us, we call you. And yeah, this is a basic thing of reactive. So what do you need for this reactive behavior? What do you need for this reactive world? We have a lot of stuff inside the JDK. And we just have to have in mind how we have to structure now the paths or the reactions inside our application. So most core object relational or object-oriented developers have this invocation waiting doing something, and now we are not waiting, but we have no control about, okay, the result is coming sometimes, somehow, whatever. So we need not only the file mechanism, we need this collecting mechanism as well. So we can do it in two ways. So I will call in a second this observer pattern. So just I'm doing nothing until I will be invoked, then something happening, and then I'm doing nothing again. Or the other thing is I'm just pushing now, initializing and calculation, and what is the right way to sync, to wait until this result is done, because sometimes you have to merge paths, and this is more or less a tricky part of this reactive world. So just one transformation waiting, doing the next one is easy, but if you have different actions and you're waiting for different results and you have to merge this one, this is most likely then this observer hell, or this proxy hell that's just, yeah, inconvenience. But with core Java we have a few tiny things we can use very effectively, and this is more or less the first thing I want to explain, and this is called observer. Okay, one of the core pattern here is the observer. And what is an observer and how to implement this one by yourself. So you don't need an external library, you just need a concurrent hash map and a class that is just grabbing this one. So the observer will need a key and a value. So the key is more or less the registration key. So I will register with a key ABC, and then someone is able to reach me. So what I'm doing is I'm adding the recipient of this message that will be sent later, and I will register under a certain key. So The first key and the consumer that is doing this one will be given to this observer. He's holding it in a list, and if there's a value, you can say, okay, I send a value to all that registered for key A or key B. And then inside this list, you will just iterate and send this value to all the listeners here. This is one way to do it, but it's very inconvenient, so you don't need this different key. So what's more likely is that you have an observer and you have just a list of listeners inside, and then you need something to register. You have, for example, this observer. You can have it in different ways. So one observer is, for example, a non-static version that you're using, for example, in graphical user interfaces to connect different parts of your UI composition so that they can communicate to each other. So the button is sending to the observer, and the observer is then sending to the table and the label and the whatever, and they're all able to do something. So this is an non-static observer you can use inside some local constructions, whatever you need, so that independent units can interact with events. Okay, if you don't want to create this observer, or the observer is not really what we need, or we need more complex ways to connect between different streams, data streams, then we can go back to the default implementation out of the JDK, and it's called Completable Future. Completable Future is really a huge thing, and the API is just massive. So it really takes some time to get used to it in all fine details, but if you just want to ramp up and try it out, it's easier as expected in the beginning. So what is the basic idea of this Completable Future, and what could you expect? The main thing at this Completable Future is that you can define what should happen, what resources should be used, and how to combine different asynchronous calculations. So if you have this quite complex tree, so A, B and C coming in different times in different behaviors, but you need first A and B to calculate something, that's input for the combination result plus C to finally calculate what you need. For this you can use this Complete Features. Complete Features are not a process, not a thread, they are like fibers. So you have this calculation units, and this calculation units will be shared over different threads from the operating system or inside the JVM, and this will be mapped to operating system threads. So for you it's just a very, very lightweight calculation unit that will be calculated somehow in some order inside a defined resource. So how to get it? You have this class Completable Future. I need a little bit my slides here, because it's more than I can remember precisely, but you have this executor service, and to get an executor service is that you are going to the class executors and say you want to have, for example, a new fixed thread size thread pool, and you can dimension it in any way you want to have. So with this one you have an executor service. This is a resource where this work should be done, and now we want to combine the work with this executor service, and this is done with a Completable Future, and you can supply asynchronously the task you want to have, for example a supplier or whatever, and set it in combination with this pool, and you will get back a Completable Future of this type that is a return type of the calculation unit you offered. If you have now combined this task to do with a pool, and you have a Completable Future, then you can, for example, merge it with something different, and other task you want to have. So what happened here is that you're just putting the next task to do and combining it with a Completable Future that you had before, and this is now waiting, and you will get again a Completable Future. And this Completable Future, you can now wait on this one with the method join. Don't forget to shut down the Completable Futures and this executor pools, exactly the executor pools, before you try to exit your program, otherwise it could be an endless loop. But what we saw here is that you have different parts of work, and it matches perfectly with the functional world because it is an input, it must be stateless, it should be an output. And the functional world, or if you are converting first to the functions and then using these functions in combination with the completely future, you have a huge amount of possibilities for the reactive world, because reactive and functional fits perfectly together. One additional thing is that every completely future can be associated with a different pool that should be used. And the good thing here is that you really you have the possibility to fine-tune the resources you have. So how many CPU cores, how many threads, and how to map it. So this is something that you can move, so the work can be shifted between pools. And with this you can dimension pools in a way, if you have CPU intensive pools, if you have network intensive pools, and so on, because then you can dimension them completely independent. But in the main thing, the whole process can be you're just adding everything together, and you have still a quite balanced system. So this is one thing, but if you're looking at this source code, you will see that you have a lot of boilerplate code. Then combine async, then combine async, and so on and so on. And well, how to deal with this one? If you start working with a completely futures, you will see that a completely future is active immediately after defining it. But sometimes you don't want to have it. Means you need a function that is able to create a completely future for you. So if you have now functions that are creating different completely futures for you, what you could do is you can just start composing functions to compose a description of the final complete future you need. And then just after you have this function and the time is convenient for you and you have all input values now, then you can start using this function with apply. And then the resource allocated, the complete future will be created, and the return type of this function will be the final complete future. You're waiting and joining later if you want to have this result. So building complex trees of of complete futures is possible with composing functions in the right way. Okay, now what should you do as an object-oriented trained developer? Should you forget everything about design patterns and so on? No, definitely not. So if you're looking at this, building a tree out of complete futures, you will see that you have a lot of repetitive code. And just combine it, for example, with something you know, for example, with a builder pattern. So it's called completable future queue. If you are looking at the GitHub repository, I will show you here. But the main thing is that you can just use existing design pattern to structure the way to compose completable future trees, and then combining with the functional approach, so the stateless definition of transformations, this is a very powerful tool. So just create a builder pattern where you're adding function, and in the end you just say apply or build, and then you have something that is creating everything together, because now you have everything. So you can build different kind of builders with this, for example like a checked builder, or you can do it like a nested builder or whatever. So you have all the possibilities. So don't be shy, mix the approaches, don't stuck to pure functional or pure reactive or pure whatever. Just take the best out of all these worlds and make it suitable for you. So, and one example on my side is just mixing up the builder pattern with a complete future and the functions. Okay, time for the conclusion. What we learned today is how to deal with functional approaches inside the core Java language without adding any dependency. So we looked at currying, memoizing, and all other basic principles for the functional coding. And then we had the basic introduction to the reactive part, this observer, and later a short view to the complete future. And finally, don't be shy, mix what you ever learned with design pattern, object-oriented, functional, reactive, whatever. Mix it in a way that it fits to your needs and that it will give you the best benefit for your project. my day is done and I will go now out of the forest, and soon it will be dark, so it's time to leave. And I hope you enjoyed it. If you want to see more, then check out my YouTube channel on my YouTube channel and my webpage. There you will find a lot of stuff. You will find it in German, you will find it in English, and if you like outdoor, have a look at my bushcrafting channel. I just love it. And so far, stay safe and see you.